basically, oh yes. Um, hey guys, okay, basically, I'm looking at the project framework, but this is like the project was, doing something of the priority. So you got this document I have here on paper, but it's kind of I'm going to teach you formally. But before we start, I'm trying to build a Rift first. But the R open. So if you remember last this video, you go to repositories, you search in R open. But I'm gonna change this to R, capital R underscore open for the repository. But this is just the open repository. You can open a file. You got the DLLs, you got the dirty files, C, D, like C file, but it's a dirty file. It's an old dirty file. But you can run this repository here. You can compile this code, get the executable, also you get a compiled version. You can see from basically a target platform. But this idea, you just open the PNG, and you should get the image open. Business encoding, the encoding. But that's gonna be raw R big R, like capital R underscore open. Okay, next is next. This thing has to go. Is this thing like taking notes even? Yes, it's taking notes. So the topology framework is what it is. We've got the vortex there. What else? So today I want to illustrate policy, but I got it here on my notes here. So basically, you got like a reverse mapping for everything you do for conjugate modeling. Because Gosilang, the GS file supports polarity and conjugate modeling automatically. But what do I mean by that? It's like counterintuitive. What I mean, you don't understand what I mean. Okay, yeah. Let me give you an example. So you're trying to compute pi, number pi, but you are trying to model pi as some kind of structure, dimension. So basically here, this repository is like polarity for modeling. So you can model things any way you want it. The data can be abstract or like but the data is half true because it doesn't represent the full picture of the problem you're solving. So that's kind of the duality of the problem. So basically, you model something, you get a half. What do I mean by that? What do you mean by that? So what I mean by that is you get pi. Pi, if you want to compute pi, you can start with 3, but you can use some kind of framework to something that's round. Like you can start with number 3, but 3 is not 3.14, so you can start with an integer 3. 3. Oh, my pen ran out. It ran out. You can start with 3. You can start with 3.14. That's the idea, but I can't find my pen. I've got pencils here, useless. Guys, it's really annoying me. I'm trying to look for a pen here. Because I know something, I'm not looking for it properly. It's faulty pens, gel pens. Sorry guys, it's not working out for me tonight. I did prepare for the pen, not the pen around. Anyway, Andy. So the thing about this, you get the system of pi starting from pi 3.14. But pi 3.14 is not enough for you to compute the full pi precision, like quickly. If you start with 3, it's not 3.14, but you can accumulate values to add to it. Or you can start with 3.14, you can reduce the values to get to it. Look at my pens here now. What do I mean by that? Where am I going with this? Where I'm going with this is 3.14. The type of number 3.14, it can be split into 2. If 3.14 is the full number, you get 3, which is just the integer, and you get 0.14. 0.14, let me try to find pi. Type in pi, enter. So pi is the floating point to 3 decimal places is 3.141. But 3 just 3.00. But 3 just 3 with the 3 fractional parts of 0.00 dot 0f. Dot 0, 0, 0, like a dot 3f. Now, the dot 3f is with the 3, but with nothing, with a nil or 0 representation of dot 3.5, which just means 3 zeros after it. But you can get the same thing as the other ends. You can get dot 1, 4, 1 for 1, and you get some kind of number 3 before it, so you can get 0, 0, 0. But 0, 3 unsigned, you get 3 unsigned units before it, and that'll be 0, 0, 0. But the problem with this is the bidirectional casting. So if I'm working with the computation of 1 for 1, the 1 for 1, that's for schema as dot 1, 0, 0, 0, f ready. But that's closer to the 10, one of the tens, one of the units, 10 to 100. So that'll be one of a TF. But basically, this is a format from schema for it. It's not really a schema, it's a standardized model, which goes on, let me do. Basically, this 1 over UTH is the unit conjugate model. So if I have 1 over UTH, then I definitely have, because this is like a model of it. So I can start with units, 1 unit, 1/10, 1/10, and 1,000, 100. So 100. So I can do dot 147, or I can do 3 here in the units model, or 0 here in the tens model, or 0 or 3. Basically like a sparse model. 0 or 3, depending on how on the computer. And then the tens model I get 3 or 0, because there's no 3. And 100 model I get 0 or 3. No 3, because I usually get 0 here. So the zeros are just epsilon states, because they just have kind of question. So I'm saying, so it's like 100, it's like a model of like tenth, but this is just January. So this is like the January system of 10, because you count in tens, we count in ones, but ones be tens. So it's not really universal here in computer. So the same thing you have in binary, for conjugate system. So it's like union modeling, but it's like incremental. You can go for like 0.01, but it doesn't really make any sense. So the binary equivalent of this 3.14 7 to 2 to the binary equivalent is the floating point position. So let me try to find it here. I can go on offside here. Basically, get this is binary. So what's number 3 in binary? 3 in binary is 0, 1, 1. From the left you get 0, 1, 2. And that's the 3. This 3 this is rubbish, but you get dot 1, 4. So how would you represent this fractional system? Dot 1, 4. So I can take the unit model. That's I see 147 here, but this will be the inverse. You get 1 over 147, which is equal to 147 divided by 100. So this will be 0, 0, 1, 2, 3. This will be 0.147. So this unit is over 100. So this is the unit model. So but unit is a 100, 1 over 10. So the 10th will be units of 10. So this 110 will be 1 over 10, 1 over 1, 1 over 1, 1 unit of it. It's not so the field. So this 1 over 1 is unit. So that'll be 1 over 1. You get 1 over 10, and then you get 1 over 100. Now this will compute back. So you get the place of that 1, 100, the 10 of 1 unit, 1 entire unit, and then 1, and then to get a 4, you do the other one. You get 4, 40. That'll be 1 over 40, and then you get 1 over 700. So you get it like this. So this is what I'm saying to you guys. It's like yeah. So basically, guys, you see this now? This is what you are actually using here to get it. Where am I going with this now again? So the problem I'm trying to address here formally is the type system, because when you're using the addition in January, you get to the same January in a binary. So for me to convert this properly, I now say 1 over 1 is 1 unit, 1 fractional unit. So this 1 fractional, this is a fractional unit. So this would be dot 1f to 1 fractional unit. But if I go to dot 10f, I have to do dot 2f. But this dot 2f means what? 2 fractional units. And that will be the January equivalent of 10th, 1 over 10th. And that will give me 40, 1 over 40, 1 over 40. And the third fractional unit is the same thing, 1 over 100, over 700 for 147. So if I compute this properly in binary, I have to do it like this: 1 over 10. No, basically 1 over 1 is 1. 1. Because it's 1. It's not 1 over 2. But in binary, the number 1 is 0 on the left side, and then 1 on the right side. So you get like a 1, 0, 1. So you get 1. So this is 0, 1 in binary from left to right. The 10th is the same thing, 1 over 40. But 1 over 40 is 1 divided by 40 is 0.4. Basically, I use my calculator to do it. So 1 over 40, 1 divided by 4 is what? 0.5. 1 divided by 40 is 0.025. 0.025. Now, this 0.25 is 1 over 40. So I now get the 0.25, but I need to calculate 25. So basically, the number 25 in this is 25 to the binary. That'll be so I need to be negative number. So I have 0, 0. Basically, I get 0, 0, and get 1, 2. 1, 0, 1, 2, 4, 6, 8. 1, 2, 3, 4, 5. So you get how many do I need? 25 divided by 8 is what? 25 minus 8 divided by 8 is what? Minus 8. So basically 1, 2, 3, 4, 5, 6, 10. So you get 25 divided by 10. So you get 2 tens. So that'll be 2 tens in 8-bit mod 8. So if I do 25, 25 mod 8, what will be left? 25 mod 8 mod 8. I'm giving it. I get 1 remainder. Now, 1 remainder cannot go 25 mod 8. 1, 2, 3, 4, 5, 6. Basically, if I have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So I get 2, 4, 6, 8. So I get 24 modulo 8 will be 1, but that's with 1 remainder at the other end. But 24, obviously, I got to get 14. So I get 14, 1. 25 minus 14 is what? 25 minus 14. So 25 minus 14 is 11. So I get 11 left. Now, 11. So I now complete 11. So I leave 1 in 0 total. 11. Now, 10 and 1. So I get 0, 0, 0, 0. So I get the binary number of 1, 0, 1, 0, 0, 0, 0, 1, 0, dot 1. Dot 1? Yes, because dot 1 is unsigned. Wait, 1, 2, 3, 4, 5, 6, 7, 8. Yes, 8. But I get assigned 8 of dot 1, which is a remainder of dot 1. But this remainder of 1 can be the assigned integer. The signed integer, just like we get like a 1 because it's unsigned. It's unassigned. So it's like a negative number. So you get the negative split to negative unsigned. It's not assigned. It's signed, but it's fraction size. So you get 1, the entire 1 unit over. So you get the binary number of 0, 1 over 0, basically 0, 1, 0, which is equal to 1 over 1, 0, 1, 0, 0, 0, 0, 1. This would be 40. The number 40. 1 over 40. The fractional equivalent. The same thing with the 700. So the 70, 700. So get the 100. So 1000. So if I do 1 over 700, 1 over 7 is what? 7 in binary. So you get like 7 in binary is 6, 1, 6, 7. So you get 6, 1, 0, 0, 1. But this is 7. So you get 1 700 will be the 1, 0, 0, 1. That'll be 1 over 7. That'll be like 10 over 700. 10 over, because in binary. But this is 1 over 7. But 700 will have to be 2 more zeros. So you have to times by 100. So if I do 1100 times 100, that 100 will be 10, shifting to 10. So I have to left shift, because left shift is like shifting by 2 tenths to binary epsilon state. which would be 2, because you use left shift for right shift. So if you want to get to the right, you have to use the full left shift. So you have to get everything on one side, and that'll be 0 the size. For example, I can give you example how I do it. So let me give you two instead. So this will be 2 left shift. So this 2 4 will be 1 0 0 1 for 7, which equals to 7. But you know, I shifted twice, so I have to double the size of the red 10. So if I get a tenth, which is 1 0, I add 1 0 at the other end, you know. So I have now 1 0 0 1 plus a tenth of it, no, times a tenth of it. But I double this tenth, so 10 times 10 is 100. So 10 plus 10 times 10 times 10 will be 0, 1, 1. 0 times 0 is 0. 0 times 1 is 1, 0. And that would be 1 times 1, 0, 0. And that would be 1. So you get 1, 0, 0, 0. And that would be a tenth, 100, 10 times 10 is 100. So the 1, 0, 0, 1 times 1 0, basically plus will be 1 0 1 0 0, and that will be a total of 1 0 0 1. Because you know times. Basically, get this number 1 0 0 1 1 0 0 0 to be 700. So that's the idea. I was going to say. So the idea of this, the problem I'm having with this framework is, you know, you can complete in real time, but it doesn't really align with the text system. But you know, the text system is flexible enough to handle the conjugate pair too. So for example, if I'm trying to compute from plus, from plus for negative dot 35, I have to flip the on sign. But this is the point problem addressed, so I have to flip the on sign. So this is what I'm saying to you guys here. This is what I've got so far. But I need a new one to do it. So just look at it, guys. You can see everything there. So let me try to do it properly again. So the thing I'm saying that so you get the 0 1 from the left as a what? 0 1 is equals to 1, and then you get the 40, which is equal to 1 over 10. No, 1 over 1 unit, and then you get the other one, the 40th one, which is equal to 0.147. But 0.147 is yes, 0.147 is like the 10. So you get the number plus or minus, depending on the sign, of 101000010, and that's 0.140. This is like 40. So this is my tenth. This unit is 10th, the standard 10th, and you get the 40th. That's 40th, 0.40, and you get the 1 over 700. So you get 1 over 47, 1 over 7. You get 1 over 7. So 1 over 700 will be 100110000 in pattern. For both pairs of plus or minus, if you just have the left bit conscious switch via it. So this is 3.14, which would be 0 1 0 wait 1 1 0 no 1 0 1 from the left. So now the right shift. Now 101 is like from right. Now what is right shift? So right shifting is very important here to do. So right shifting, when you right shift, you have the right length of the whole thing. So if I right shift 0 bytes, if I right shift once, I'm getting one dimension of it. You know, because you know right shifting is like the size of it. Just think of the length of it. So the size equals the length. So for example, what I'm doing with this in the whole framework. So if I have two squares, 50 centimeters cubed, and then 125 centimeters. Because we'll do some maths now. So 25 centimeters is split into 5 times 5, 25. But you get 50 centimeters, which is 50 divided by 3. So 50 divided by cubed, the square root of 50. Look, let me do this properly. So so you get the standard squared, 5 times 5 times 5. Length times width times height. This is 5 times 5 is 25. Now 25 is just 3 times 5 is 225 times 5 is 25. 10, 11, 12. You get 127 centimeters cubed for this volume. So the volume cube fastness to the power of 3 represents 105 centimeters cubed. But it's a dimension, these are all dimensions. So when you are right shifting, you are getting the dimension each time you right shift. For example, you are like so if you want to get, so if I have the number 5, how do I do it now? The number 5 is what? In binary. So that's in binary, it gets a 0, 1, 2, 4. So I get a 1, 0, 1, 5. Now this 1, 0, no, 1, 2, 4. So 1, 2, 4 is 1, 0, 1. So 1, 0, 1, I get 5. I do 1, 0, 1 times 5 times 1, 0, 1. I should get to 200 and 200 and again 200 125. Sorry, 125 meters, centimeters. But this is cube. So if I do 1 times 1 times length times width times height, I get this. So this should be 1 times 1 times 1 is 1. Then you get 0 times 1 times 1. Basically, try 1 times 0. 1 times 0 is 0, 0. 1 times 1 is 1. And then you get 0 times 1 is 1 on the left side. And then 0 times 0 is 1. 0 times 1 is 1. 0. And then you get here you get 1 times this one. So you have a plus this one, and that will equal 1, 1, or 1, 0. And then you do the other one. So this one is done. And then you get this one, doing this one. So you have to, you get like 1, stage 1.2, stage 2, index 0. So you get indexes here. So you get 1 times 1. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. Done. And you get 0 times 0 times 1. 0 times 1 is 0. 0 times 0 is 0. 0 times 1 is 0. And you get what? You add this up, you get 1, 2, 1. 1 plus 1 is 1. Carry the 1. And then you get 0, and you get 1, 1, 0. And this is a good stage 3. So you get the number 0, 1, 1, 0, 1, 0. That will be stage 3. And that will be times, so you get the last set to distribute. So the last set will be the last group. So I've done this ij. Now I've got this jk. So I get this one to do. So I now do the other 5. So I do 5 and 5. Now I do 5 and 5. So this is now do 101 times 101. So equals 101. And that will be 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. 1 times 0 times 1 is 0. 1 0 times 0 is 0. 1 times 1 0 1 is 0. And you get plus 1 times 1 is 1. And then 1 times 0 is 0. And then 1 times 1 is 1. And then you get 1 0. 1 plus 1 is 2. But I don't put 2 down. I write down a 1. And I carry the 1. So and I get 1, 2, 3. Now I get 3. But I don't write the 0 because it's binary. I write 1. Now 2, 3. Now I get 2. Now 1 plus 2 is 3. Now that'll be 3 here. So 3 here is 1, 0, no 1. No, you get 0, 1, 1. So this will be 0, 1, 1. You get 1, 0, 0, 1, 1, 0, 1, 1, 0, 1 plus the 1, 1, 1, 1, 0. And that's so 1 plus 1 is 1, 1, 1, 2. This will be 2, 2. Carry the 1, 1, 2, 1, 2, 3, 3. Now the 3 will be 1 plus 3 plus 1. That'll be 1, 2, 2. That will call 2. Now it'll be 1, 1. That'll be 3 here. That'll be 3 here. That'll be 3 here. So you get 1. 1 plus 1 is 2. Now you get 1. Now you get another 3. Now you get 3. That'll be 0, 1, 0, 1. 0, 1, 0, 1. And that'll be 1, 1, 0. That'll be 2. That'll be, so 2 numbers get 1, 1, 0, 1, 1, 1, 1, 1, 1. So basically, this is the binary equivalent of the number 125 in binary cube. But this just represents the segment of memory. That's the problem. So to segment the memory is split into the segment itself. So what I mean by that, in this partition, this operation that I have to define that that unifies them via lattice modeling. So there's a lattice here that can get the number 5 in a segment, and that 5 is unique to one x y dimension. So if I now right shift, like I was pointing to the right, I should get this 5 segments of memory if I polarize it correctly. You know what I'm saying? But what I mean is, I mean like 100 divided by 5, 125 divided by 5 should give me one full dimension of it. Two full dimensions of it. So where's my calculator? 125 divided by 5. That'll be 25. Now, 125 divided by 5 is 25, equal to 25. Now, 25 means what? 25 means centimeters cubed. Now, that's 25 meters cubed. That's the first. If I shift it, I should get. If I shift it twice, that'll be I get the size of 2 dimensions, x and y. But this time, between 2.5 dimensions, it doesn't really matter. So you get 2 dimensions. So you get if I shift it 2 dimensions, I should get a number 5. 5, because they're 125 divided by 5 times 2. 5 cubed is 2 dimensions, 25. So I'm shooting by 25 already. So that's the idea of it gives you the size, but a dimension of the size. Let me try to find it now. Let me try to show my work here. So what do I mean by that? So I get a binary calculator. Here. So I get the binary calculator here. We get the binary calculator here. So I get the binary calculator. I get the current. So I do 125. Oh, I get the binary calculator. So I do 11011. 111, and that'll be divided by the binary equivalent of 25, which is 25 in binary is 5 and 5. So that'll be 25. But this is like 25. 25 would be the 25 would be 5 times 5, and that should give me 0. 1, 2, 4, 5. That would be 101. So it would be 101 plus 5 times 101 is what? 1. Carry the 1, and that would be 1, 1. That would be 1, 1. That would be 1. So you get 111 is 5. So 111 will give me 225. Anyway, basically, you get if you have 2 axes, you get if I divide 125 by 5, the decimal value is what convert back to decimal. So basically, the binary to decimal is the same thing. So you get convert decimal to binary. So you get 125 to binary. Basically, you get 125 in binary is what 125 in binary is what? Basically, 125 in binary. So I guess I'm trying to get it properly so I don't mess up. So I want to choose something. So 125 in binary is a segment of it's a 0B 111 1101, and then we get a 5 in binary. This is 25. This is 125. 5 in binary is 0. 5 is 0B101 because it's the binary relation, and you get to the 5 in binary, which would be 25 would be 0B1101. So if you do the right shift, the left shift once, the right shift, which is like the right shift 0, that will give you the length of the whole thing, but as a scalar. So it'd be like 125 centimeters. But it won't be cube. But if you shift 125 centimeters cube over 5 times 5 times 5, 3 distribution, which would equal 125, right shift 3. 3. So 125 right shift 3. 3. And that will give me 5. So this would be basically this would be 3 right shifts. So it will be 2, 3. You can basically a math calculator. 105 right shift. Sorry, shift right 3. Uh, 105 right shift. So basically, I'm trying to binary bitwise calculator. I'm trying to find a bitwise calculator. Right shift. So Bishop Omni calculator is what I found. 1 second, guys. So I get better binary data, and then we get left, right. So right shift would be. So basically, left shift goes in, makes the number bigger. Right shift makes the number smaller. So we get how do I calculate? But I don't find the calculator itself. So I do 105, 105 divided by 2. The what's 2, and that would be what's left of 2 will be the result of it. Because you get it here. 105 divided by 2 divided by 25 will give me 5. So it'll be 5. So because there's x and y dimensions directly. So whatever you get from the result is what you get keep in the division, because it depends on the dimension you're working in. Divided by 2 in division. So you get that there. But where is that going with this now? So why this matters for the ref. So basically the idea I'm telling you guys is like new. You get this here. It's new because it works in dimensions or the size or the magnitude. If you get the magnitude, you gain 1 unit dimension. But the magnitude is like the conjugate inverse. So the magnitude is just the size, which is scalar. But if you get one of a scalar, that's a fractional unit. So the size is the whole thing, but the magnitude is just 1 unit of the whole thing, and that's what's called a unit model. And the universal model is just you get 1 over the conjugate unit, and that will be the fractional. What you're doing for that model, it goes up and down by the 10th hundredth, and the binary system you represented it in. Yeah. So that's the idea there. So basically, you get 25 centimeters cubed, which is a square, and you get then you get the other one 125 meters cubed. And this is like real number. So the idea how you can give a kind of framework is like literally 25. So you have like a 2 sliding box. One big box is 125 volume, 125, and you get 1 in 25. Now 25 centimeters seems like a small one because 5 is 5, but that's not the idea here. The idea is there's a proportion between 25 and 125, which is like 1 to 3, 2 to 3. So basically, how you can compute that with framework is like you have the sliding boxes. One big box, one small box goes faster, hits the wall, and basically it's just with a big box, and the box goes farther. You get but the number that computes is infinite, because you can get 3.1415 all the numbers of pi with infinite precision. But infinite precision is just one type of precision, so you can get uncountable infinite precision and so on. Because you're working on units, you're working on basically when you have the scalar one, the unit one, you get uncountable precision. So that's what I'm saying. Gosilang is going to do. So it's like the caste system here, which I'm talking about. Now, what is this caste system? Now, the caste system is like really casting. So you get the main caste system here for casting, which is so basically this is the one I'm saying. So you see you have some arbitrary computation you want to compute. So see this function here. So you get the thing there, an array. So you have like a model of caste. So you get the type of model. So in Gosilang, you have like say you want to define an array of but you want to index the thing via biological informatics. So you already know what's in there. So the problem with information is you don't get the full picture. You have to go through many functions so you can get through a function process. So that's the kind of problem there. So the problem I'm saying is that the function let array a equals for one array. Is a number 1, 5, 2, 2, 6, 1, 5, 2, 10. So basically in Gosilang you have a let keyword and then you give a colon equals. This means set the token type and the value equal to an array. Now this array is like a sparse array. It's like a sparse DM model. This is an array of DM, but this can be the same as array token type, token meaning. Basically, you can have an array you can have a list, 1 to 1, 5 to thing. You can have a slice, but you can't. You can have a slice, a splice, but you can't have a splice. For example, you can define uh, a a splice. Sorry, a let a index let I equals to the type of value, the type of value, the type being the index. Some kind of I is an index already, but you set the type of index to a vector. The vector is the index I index value array. Now IVA. So basically, you index it with the system. So I is just some kind of index range, which is the whole goal of this. Yeah. So the I is just a number. You are indexing the array, which is 5 letters. But the main problem here is there's a kind of model of U entity there. So you see the U of 32 is like unsigned in 32 of the data structure, and the 32 int is like 32 bits of floating point numbers. We can have 32 bits in dynamic time. So if I type in let U let let A, okay, let's say V, let's say V equals U type of the Walsh operator, like the colon equals syntax, colon equals U32 type. You put an array of 5 elements. Now this array of 5 elements is like only 5 minutes allowed maximum, but it's not variadic, so it's just a static set system. There. So you get let AI. So V is an index of type of value U, but it's a nil, so we don't know. Unsigned integer, unsigned int32 integer containing 5 bytes of data, 5 memory, 5 memory locations set. It's not a vector form, and you can do this too with a tuple. So you can U32 and you put a round curly braces and you put 5. It should be like a 5 tuple, something like an index and ordered, index and unordered and index, index and basically unordered and index. It doesn't matter order. You can put like U let VW x U equals U colon insect colon equals U32 T. Now right brackets T. Now, but you get the right brackets, which means like this one's basically the standard model for. So you get because it's an index, use an index, you get U32. But this U32 is basically my thing just like started playing up, guys. So this is like a model here, so you guys can see it here, guys. So you get this U32. But this U32 has an index too. So the U32 can be because you get the inverse one. So you get the canonical. So basically the canonical will look the same. So you get I for index, V for valid, index or key, I for like the splice, the data splice. So the data splice is the range. So the range is like start, stop, skip. So that's when you're indexing. So if I'm trying to look to an array of 1, 5, 7, 1, 5, 2, 26, and 10, 1, 5, and I want to start at 0, 1, index 1. I put a splice of array, like 1, 1, colon, 1, start, stop, 1, 2, 3, stop at 3. So 1 colon 3, and then you put another colon, and then if you want to skip a step of 1. So, but if I want to keep it busy, I can put a colon for start and stop, but I can skip a step of 1, so I can skip the second index. But that's start stopping. So this is like the data I want to get. Let U equals colon equals U32, and then you get the right bracket, which is like the stop range, and that'll be 1 colon 3. But if it's an array, it's variadic. If it's a tuple, it's indexable, and if it's like an object, you do you do like a map. So you do like an object, you get like a dictionary, you get like a curly braces, you get so you get like some kind of the key bound thing. But come on, does like this. So you get 1:3, 1:3. That. So what does lost key value? So you get the value. So the value of this is you get. So I is like a the subset. So if I just have let u equals sine 32 of some kind of cost method, v, I can get 1, 2, 3. So that would give me what? What would this be? This would be the clone of a, but it would just be 5 to 26. You know, but it's an array. Depending on how I structure the data in memory, so it copies down without failing into the set. And I can do some operation on it using the subset. So if I now want to like get a data out, I get that model to get a data out. But there's a one more problem on this because you get to have the inverse to pointer to the system. So what does the pointer mean, guys? So you get the pointer meaning like the lambda model. So if I want to set the target, I just want to observe it and consume it, which I'm saying. So it's actively knowing the state without obviously on the fly without being told to do it. So how would this work with the conjugate inverse model for it? So you get the conjugate inverse. You get let's define a setup. Let's setup. Let underscore setup can be because it's a meta program. Let setup equals to lambda 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 index. So the index notation will be the point where the function is transposed. So if you get the array, let u equals colon equals the copy equals v equals a but you put the a left bracket u32 1 to 1 1 to 3 1:3 start stop range but you into the 2 and then you get a setup index value. The value is what? 1, 2, 3 start index value. So basically this is star range start stop but it's like all in one. The value is what? The value of this rate. Basically the value is just what you add to it, so you get so you have like an initial rate of like 10, 20, 20, 20, 20, 12, 20 number 20, 12, and the array is like the full information should like the accumulator or the incrementer. So it's like if I want to process on the full information, so the if I want to increment it, I just say put this kind of like an underscore, but I don't have to put anything there. I can put this on underscore, but it's a nil operator. It's like nothing I'm doing with it. It's like a nil, like a placeholder nil, which is like no memory, no type, no value, and that's like a nil iota state because you don't need the information to process it. You just put empty. If it gets too variadic, at the end, and you just wanna ignore it. There's nothing you do with it. Yeah. So that's kind of the idea I'm building. So what's my numbers here? I chose. We'll start again. So no, I don't have to start again. No. So the the setup. So if I need to set up to set a value, I have to update it. So this will be the function you're mapping to. So the auto will be like so the setup will be let setup include, so the accumulator will be whether the function is transformed. So let setup equals lambda take a lambda function that maps between two lambda lambda that takes two inputs list A and list B, and then perform some kind of clamp operation between the accumulator value. So this can be any function you define with the placeholder z. Because it's a flexible type system. Basically, you don't have any fragmentation because there's a mapping between the bidirectional systems. That's the goal. So you get lambda So basically, you get the floating point operation. So this is like the index value array, and the array will be like a index value. The value will be the array, and you get the array index and the value index in the other one. Because you can start with the data, that's the full array. If you start with the value, that's what you're gonna add to it, increment it, and you get the thing. And it's gonna map to the function. It's gonna be binding automatically. So the function has a bind variable. So the index is like the array is the full data. So I can just take this. If I just know data there, basically the full data will be. If I want basically, I don't even need the last one from this the underscore. So let's. So basically, this is what I'm saying. This is basically one dot here so far. So you see, like there's a thing there. So if I wanted to do, I could just define this let let b because a b be the copy of a colon equals a but a has some kind of double namespace. So I can do a colon join which is like a lattice join, or I can do a colon because you know like a namespace model that's universal, and this string. Now, and a colon, which is like on the namespace, you know, a colon, what? Intersection. So, where the two meet. So, intersection. So, this is like the join. This is what the lattice system is going to do. So, if I want to join A to something and get a joint pair between 2, A and what? U. Now, A and U equals B will mean that B copies all of A without just by pointing to it, by copying the subset of biological information. Because you know, you get half truths in your processing, you don't have all the information. So this is what the axiom is meant to do. So the idea is to like have this axiom to universal to get the model. So if B is a clone of X, if X I can do A colon clone, I can do A colon copy. But you know, if I copy a reference, I copy the pointer and everything, and here's a pointer and a reference to that object. So if I mutate A, B, I mutate A, the state of A, and everything A. But if I mutate B, I don't mutate A if it's copied on clone. So that's the idea. If I clone it, I get a full copy, but I don't have reference to it, the old one, you know, via the memory model or something. So that's the idea. So A colon join B U is if I put a placeholder underscore, I don't have any more reference to it. But that's the standard one, so I just like set the token and type the value without a pointer to A. So let U equals colon equals A, left bracket U for unsigned integer. There are two bits of memory. To do by range 1 to 3,